Welcome to a new episode on my exercise series Introduction to Physics. Last time we've been talking about how pressure, volume and temperature relate to one another, for example in an ideal gas. And yes, this is part of thermodynamics, but what we haven't been talking about is actually about a very important subject, which is the thermodynamic cycle. And in order to do this, we have to take a closer look at the first law of thermodynamics. And this is what we are going to do today. So let's start. An ideal diatomic gas goes through the following cycle between two heat stores of temperatures θ1 equals 500 degrees Celsius and θ2 equals 25 degrees Celsius. First, isothermal expansion from V1 equals 1 liter to V2 equals 4 liter. Secondly, isochoric cooling. Third, isothermal compression back to V1. And last but not least, isochoric warming. How large are heat input and output for a gas of mass m equals 5 gram and specific gas constant Rs equals 288.2 joule per kilogram and Kelvin? Out of this, we can take the following information. We have given two different temperatures, θ1 as 500 degrees Celsius and θ2 as 25 degrees Celsius. Of course, degrees Celsius is not a basic unit, so let's convert it right here. θ1 becomes T1 equals 773.15 Kelvin and θ2, the 25 degrees Celsius, become 298.15 Kelvin. In addition, we have given two volumes, V1 as 1 liter and V2 as 4 liter. Again, liter is not a basic unit, so also let's convert it right here. In order to do this, we have to multiply both values by 10 to the power of minus 3. Then we have them in meters to the power of 3, so meters cubed. In addition, we have given the mass m as 5 gram, also not a basic unit, which is 0.005 kilogram, and we have given Rs as 288.2 joule per kilogram and Kelvin. And actually we are looking for the heat input and output. But what does it look like in a sketch? Usually when you are talking about thermodynamic cycles, you may want to plot the pressure P versus the volume V. This type of PV diagram looks for the cycle that we've just been talking about like this. So first we have this isothermal expansion where the volume increases at a constant temperature T1. Then we do have the isochoric cooling where the temperature is reduced to T2 under a constant volume. And then we go back also isothermally, we are keeping the temperature and reducing the volume. And finally again isochoric heating, which means we are increasing the temperature from T2 back to T1 under a constant volume again. Now, what does this mean with respect to heat input and output? When we're talking about an isothermal expansion, meaning the temperature stays constant, nevertheless, we will see that we need some heat input in order to increase the volume. Regarding the reduction in temperature from T1 to T2 in the second regime, we'll see that there is some heat output. And also, when we keep temperature constant then at T2 and reduce the volume again, we also have an heat output. Whereas keeping the volume constant finally in the fourth regime and increasing the temperature needs a heat input. And this is not all that we can take out of this diagram. Of course, this is just a sketch, so the values are not real that are given here. But what we know is that when we go around this blue curve, the area under the curve is always the work. So for region 1 means, yes, there is a very distinct area between the blue curve and the horizontal v-axis. And also for the third regime, where we are at temperature T2, there is a very distinct area. On the other hand, for the two isochoric processes, there is no area at all. So they do not contribute. But you can still calculate the total work that you get out of the process, which is the gray area that is indicated right here. But of course, this isn't even asked. So this is additional information. What we want to know is the 4 Q's that I indicated here. Q in and Q out, the input and output. How do we approach this? Well, first of all, we need the first law of thermodynamics. And this states that the total energy of an isolated system is constant. Hence, energy can only be transformed from one form to another, but can neither be created nor can it be destroyed. And yes, we can write this down. Delta U equals Q plus W. Delta U is the change in internal energy of a closed system. Q is the energy supplied to the system or that comes from the system as heat. And W is the thermodynamic work done to or actually by the system. Now, the following general definition applies to the science, because I was just mentioning that the thermodynamic work can be done to the system or by the system actually. And it goes like this. The work done on the system or the heat supplied to the system get a positive sign. The inner energy then increases. On the other hand, all the work done by the system or the heat given off the system get a negative sign. The inner energy, in this case, gets smaller. Now, of course, writing down delta U as Q plus W is a very basic equation. If we want to take it literally and go to better physics, we would write du equals dq minus p dv. Then du is still, as mentioned before, the change in the internal energy of the closed system, and it can be calculated as m times Cv times dt. Cv here is the specific heat capacity under constant volume. Of course, m is the mass and dt is the change in temperature. In addition, P is the pressure and dV the change in volume. And actually, we want to calculate this precisely for the cycle that we've seen before. So let's do it step by step for each of the 4 distinct process parts. First of all, we said we have isothermal expansion, meaning isothermal, the temperature is constant, and expansion meaning the volume increases. A constant temperature, T equals constant, means that dt, the change in temperature, is 0. However, if the change in temperature is 0, this means that the change in the inner energy is also 0. du equals 0. Hence, Q in this process 1 equals minus W in this process 1. Can we calculate this directly? Yes, we can. We only have to use the ideal gas law. That one we've seen before in the previous exercise. It states that pressure P multiplied with volume V equals nRT or mRS T. And yes, the work done is always the integral over P dV. It's always defined negative, so it's minus integral from V1 to V2 P dV. And yes, then we can actually take the equation Q1 as minus W1 and substitute W1, which means that Q1 equals the integral from V1 to V2 over P dV. We substitute P by M RS T1 divided by V. And yes, we can actually calculate the integral, right? It's not that bad. M, RS and T1 are constants. They do not depend on the volume, so we can take them as a prefactor. And the only thing that we have to do is form the integral over 1 over V dV. And this integral is always the natural logarithm of V. And then we have to take the boundaries V1 and V2, and such an integral is always using the ln that we've just calculated, ln V, from the upper boundary minus ln V from the lower boundary. So it's ln V2 minus ln V1. But wait, I didn't write this here, right? So it's Q1 equals M RS T1, which I said are prefactors, but then I'm writing ln V2 divided by V1. And yes, I did this on purpose, because think about it. Calculating the natural logarithm from a volume is a bit tricky, because if you calculate ln from, say, a meter cubed, what unit will you get out of it? The logarithm of meters cubed? This would be very strange. So we are using mathematics, and the natural logarithm of a variable a minus the natural logarithm of a variable b is the same as the natural logarithm of a divided by b. So I've just substituted it, and now it's really easy, because you can see on the right hand side just the natural logarithm of v2 divided by v1, and as long as they both have the same unit, you don't have to even care about the unit right here. So we can take all our given variables in their basic units and put them right into the equation. And you can see that we had these 5 grams that we had recalculated into kilograms. Then we had given RS and T1, where we had already recalculated T1 into Kelvin. So you can see Kelvin is going to cancel out. And on the right hand side, the last term is ln V2 divided by V1. And you can see here, well, yes, we recalculated both volumes from liter into meters cubed, which apparently we didn't need to, but, well, it doesn't matter, right? As long as we recalculated it correctly, it will give the same result. So meters cubed will cancel each other out, the kilogram will cancel out, and Kelvin will cancel out. So what's left over is going to be joule, which is actually the unit of heat or energy. So let's put the values into our calculator, and what we get is that Q1 equals 1544.5 joule. And yes, this has a positive sign. And if you remember the slide where we've shown the sketch, you may remember that I put there Q in. And yes, this means it's positive. We have to supply some heat to the system in order to keep the temperature constant while increasing the volume. Now, what about the second part? We said in the second part there is isochoric cooling. Isochoric meaning constant volume, V equals constant, which means that dV equals 0 and therewith W, the work, is 0. Which agrees with what I've mentioned earlier, that the work is always the area under the curve, and yes, if we are actually plotting a vertical line, there is no area under this line. So it makes sense. Cooling means that our temperature is going to decrease. Hence, Q2 equals du. And for du, we can use the before mentioned equation, which relates du to m times Cv, the specific heat capacity under a constant volume, multiplied with the change in temperature. And since there is, say, a strict temperature change, we do not follow, say, a certain path. We are just interested in before and after. So we can take Q2 as m Cv delta T. What is Cv here? Because this actually wasn't given. Well, Cv is more or less a constant. For any monoatomic gas, Cv equals 3/2 multiplied with Rs, the specific gas constant. On the other hand, for any diatomic gas, Cv is 5 divided by 2 multiplied with Rs. So we have to take this. And if we put this into our equation, we know that Q2 equals 5 divided by 2 m Rs delta T. And yes, those three variables on the right hand side are given, so we can take them again in their basic units. And if we calculate delta T as final temperature minus initial temperature, we are getting a negative sign. So all in all, we get that Q2 equals minus 1711.2 joule. So not a positive but a negative sign, which means that we are not supplying heat to the system, but we are getting heat from the system. So after considering isothermal and an isochoric change, we are going back. But first of all, in the third regime, we are considering an isothermal compression. Meaning again, we have a constant temperature. Therewith, Q in regime 3, Q3, equals minus W3. And yes, we only have to substitute the variables that we've seen before in this equation with the ones that are important here. We have the mass m, we have still our specific gas constant Rs, but in this particular case, we are at temperature T2. Before it was T1 in regime 1, here it's T2. And the natural logarithm goes, in this case, from V2 back to the lower volume V1. So it's ln V1 divided by V2. And if we take all our given variables, put them right into this equation, we can calculate Q3 as minus 595.6 joule. And also the fourth regime is really easy now, because we've done such an isochoric change before. Only in this case it's isochoric warming and not cooling. But still, the volume is constant, meaning W, the work, is 0, hence Q4 equals du in this case. And du in this special case is still 5/2 multiplied with m, Rs, and delta T. Only in this special case, delta T is now positive because we are actually increasing the temperature, meaning we are taking the higher temperature minus the lower temperature. So we are getting a positive sign. Hence, Q4 equals 1711.2 joule. Are we done? No. Actually, we were not looking for the separate values. We were looking for the total heat input and output. So let's put all of them together. You can see here the 4 different values for Q for the 4 different regimes. And yes, the positive signs are inputs, the negative signs are outputs. And what you can see actually is quite interesting, because regarding the isochoric cooling and the isochoric warming, regime 2 and regime 4, you see that it's basically the same value, just the sign has been changing. But we have to take all of it into account, including the signs. So in order to calculate the heat input, we're going to take Q1 and Q4 and add them up. And for the heat output, we'll take Q2 and Q3 and add them up. And what we get is that heat input Qin equals 3255.7 joule, and heat output is minus 2306.8 joule. So all in all, I hope you just saw that such a complex thermodynamic cycle contains heat input as well as output. So we have to put something into the system, but we also get something out. And of course, what we may want to get out is the work that we haven't been talking about much in this exercise, but of course it's an important part of such a thermodynamic cycle. And I hope this example helped you understand thermodynamics a bit better, and if it did, I would be most happy if you like, subscribe and leave a comment below. If you have some questions, please leave a comment below. Let me know about it, and I hope to see you soon for the next video. Bye!